It's all carbon stabilization of organics with no exception. We're interested to hear about you. And this is a comment from the booth. It's a pun intended in German because coal is also money. So it's also all about money. Thank you very much for this introduction. I'm very happy that me, as a humble Austrian, also have the possibility to speak to you. And I would like to speak about my topic. Since 2012, we've had have been operating a pyrolysis facility. When I heard from Mr. Glaser at the time, our slogan is "Sun, Earth, the best soil under the sun. Can there be a better soil than ours?" That can't be. So terra preta production and pyrolysis. We produce 150 tons of biochar per year. For 10 years, we've been doing that. And we decided for a raw material paper fiber sludge because of a simple reason. It's one of the cleanest waste substances that are there in a similar quality. If you have a look at the heavy metal analysis, there's hardly anything included anymore. And you could also improve or dilute many other raw materials, although that's not allowed. You cannot dilute. If you have a paper fiber, a pure paper fiber, the carbon content is very low. 25% isn't very much. If you mix it with husks, that was our first mixture, 50-50, it's 50% carbon, which is the outcome that led to a lot of discussion if we could be EPC certifiable, because 50% at the time was the minimum. But this has changed. We learned from that experience and used many other types of waste carrying out trials. And believe it or not, any paper fiber sludge is different. If you use waste paper, you can produce paper fiber sludge that is low energy, little fiber, and if you want to pyrolyze it, you need to add a second type of waste from the paper industry. A lot of plastic, and we tried to find a mix, and we managed after many interim steps, chipping, etc. We were able to produce a nice mixture that is working in a self-sufficient manner in the reactor and produces great biochar. If you add the results, if you sum the results, I need 2 volume parts of plastic in order to have 1 part of paper fiber sludge to be able to pyrolyze it. So self-sufficient way, 30% of pyrolysed is produced, and it would have been a beautiful product, and we could have marketed it as black lime had the authorities said yes. I didn't pursue that later. I was naive enough to think that if an authority refuses it, that will remain forever. But I would not accept that today anymore, because that would have been a great product that we could have marketed. Building on these experiences, we took another step and tried something else with the agricultural college in Salzburg. The idea was, what happens if you take cellulose or pulp treated with boric acid? We take cellulose and we use it as insulating material in the houses, and the houses are teared down one day, and you try to reduce the material. Cellulose treated with boric acid in pellets with spelt husks and pyrolysed. I was surprised how well this works. That was no problem at all. We inserted it into the system and biochar comes out. And I was very happy because we managed to get this through as an additive to manure with the authority. They approved it. That is a great opportunity, or would have been. But the problem is, if you check the system afterwards and you see greenish, yellowish deposits and slagging and agglomerations that you didn't see before. And if you open the reactor because it's out of order, it's covered with dirt, but it doesn't only come from the trial, but the greenish yellowish color comes from the trial. The central tube of the cyclone disintegrates. this means that something happened. We tried to research it, and the answers were that is impossible. Attempts or trials with boric acid, that's what happens. And others said that can't happen. So we were careful afterwards, but not too careful because we tested another thing. Then we used residual waste. That was one of the most beautiful trials for me. That was very exciting. If you look at that after sorting it, when you put it all together, there are many fibers, pulp or cellulose fibers from sanitary pads and diapers, etc. Nutrient-rich material to produce high-quality products. We tried it, we chipped it, we tried it, we pyrolysed it, and it worked well. We immediately sift the product into separated different fractions. And if you have a closer look at it, in the more coarse fraction, there were 2 to 5 millimeters thick. There was a lot of glass in it. I wouldn't have expected that. And we said, okay, can we sort glass out? Yes, that is possible. And we discovered a machine not far from where we are that is able to blow out glass. So it's detected and air pushes it out of the rest of the material. And you get very pure glass, and this glass has very high quality, and you can reuse it to produce bottles because the temperatures are so low in this pyrolysis process that you end up with a very high quality. That was a very important finding. Pyrolysis of residual waste would be a first great step to separate the different sorts. And all the raw material included in the pyrolysate can be extracted with different materials, and we use it to produce bodies like troughs. That was our ideal. This pot on the left was the first attempt with a wax binding agent. It's pure residual waste produce. And then we started another trial. Opening the system again, we saw that something might have happened. We should look at it. We introduced steel plates, different types of plates, into the exhaust gas tube, and we realized that we have a material loss of 1% per hour. So in theory, in 100 hours, the system would be gone. And we find out the reason because we work with the technical college at Dinkelfeld, and they carried out many flue gas measurements. And the devil, so to speak, is chlorine and sulfur. We identified it immediately. We can remedy that by adding lime. So we added lime immediately. And it became more homogeneous with the screening system. Now we know that you can't do that in the long run. You would need to find a different technology. But the aim was to carry out the next trial right away, and it worked very well. So this is the result. Chlorine and sulfur are the elements you need to be careful with. You can add lime and can solve the problem. Every combustion engine does that, or combustion system, to keep the system functional. And it's a perfect first step towards material separation. I think there is no single waste that needs to be deposited somewhere. You can turn any raw material in great products, and pyrolysis in this can be a first step towards a perfect separation of the substances. And then we used apricot seeds. If you want to produce biochar, don't use that because it contains too much energy. That came as a surprise for me, that only 20% is the biochar yield. If you need the energy, look into that. If you need biochar, it's not an option, because then you want biochar to be the outcome. But 300 euros per ton, 300 euros per ton, that means the raw material is too expensive. So if you need to pay 300 euros per ton to produce to carry out the pyrolysis, that's too expensive. That's not an option. Yesterday, we also had a great trial that we also did. We heard about it with bones and slaughterhouse residues. You don't need to reduce it in size. The bones basically disintegrate during the process and come out and are out of the auger and are already reduced. We try to activate with many different acids and alkaline solutions to improve the ammonia absorption. Let me just give you some results. If ever you've been working with acids and alkaline solutions, it's great, just be a little careful when you do it. It's not always that evident. We tried it, and the first thing we realized after the pyrolysis, the structure of the biochar was lost. On the left-hand side, you see the sunflower seeds untreated, and on the right-hand side, treated with an alkaline solution, they disintegrated. And if you have a look at the carbon on the right-hand side, number 21 is untreated. In black, the black columns are the bones. And if you look at the carbon content, you see that there are biochars with little carbon. They were treated with phosphoric acid pre-treatment or follow-up treatment. So this is why it's not an option. And those treated with alkaline solutions, depending on the concentration, have a carbon loss of 10%, be it potassium or sodium. And if you double it, it's 10 to 15%. Doesn't matter if it's cold or warm, pre or after treatment, we lose carbon. But that doesn't really matter. If you look at the sorption capacity, you get to the baseline of the untreated biochar, and you see already that the sorption capacities have doubled. And in higher concentrations, it's even 4 times more. So this is a good option. These 13 sample, that's our activator. Ammonia is also released. It can't be bound additionally, even if you increase it. So always the same problem. If you use acids or alkaline solution in a reactor, you have problems. You can do it, but don't do it for a long time. This means the result before the treatment and is not an option to activate biochar because the system is destroyed. And after treatment is a great idea. You can achieve many things with it, and it's easily implementable. It's a continuous operation is possible. The carbon content is reduced, but other properties in some instances get better. So this was an excerpt. I already tested this presentation. It would have taken an hour, but I deleted many things. And now I'm going to speak about what we want to do in future. Our former pyrolysis reactor has been existing only in that type. It's no longer a screw. It has been rebuilt. And we are still using spelt husks and sunflower husks, no paper fiber anymore, because 3 years ago we received the approval to produce biochar, and then I didn't want to discuss that topic of biofibers. And this is why we found a very beautiful substance, a raw material. It looks like a jam sludge, but it's strawberry seeds as a kind of mud. So people don't want to have the seeds in their teeth when eating jam, and this is why it's sieved out, and we can dry it with the excessive energy. And this is a mixture of the dried strawberry seeds with sunflower husks or shells. So this is a good biochar. We can produce 300 square meters per gram and 75% carbon content. That's our status quo. This brings us to a new project. We have discovered a new material made for a simple reason. Sieve residues are there always in any composting process, because without wooden material, composting is impossible. The second reason is I work a lot with Stephen Joseph, who speaks about the char mineral complex. Pyrolysing minerals is a good idea. We heard that yesterday as well. There was a great presentation on that topic that really inspired me. So we decided for sieve residues just because they exist and because it's a great raw material and because the energy has been removed already. I can achieve a higher throughput as compared to pure wood. What is interesting is the preparation. The sieve residues are stored for 2 months. They warm up and the remaining organic detaches from the wood. After 2 months, it's sieved again, 25 millimeters. The fine fraction was retransported to rededicated for soil manufacturing. I'm sorry for that. And here, if you could have a sip of water, please. And this fine fraction, we can take out the remaining wood, and the coarse fraction is stored again for 2 months. It warms up again, and all the remaining rests of organics detach. And here you see that there are many stones for a simple reason. We don't screen compost, only the finished soil. And with the sand and clay and mud, you add stones. This means the challenge is how to take the stones out. We screen the residues again and send it through a laundry machine. The stones sink to the ground and are extracted. And this brings us to the washed residues are chipped to 30 milliliters. The first attempts consisted in producing different fractions to be able to pyrolyze it. And then I said, I don't want to separate all these fractions. I want to use 0 to 30 centimeters and send it into the reactor. And we needed a new machine that's capable of doing it. We found it. That's the first biochar that was produced in the prototype facility. And what was important to me was to have agro-bio quality according to EBC, so BAK value below 1 milligram. That's the highest quality. I think 4 is the limit for agro-bio, the threshold. I want to have less than 1, and there's just one system. Can I canvas other companies? Biomecon is the only producer of biochar that was the purest char. That was our basis. Here you see a picture of the sieve residues with the minerals attached to the product. That is the best raw material, in my opinion. This brings us to the development of the facilities. Here you see the current solution. You all know the idea originally was the degassing of material and the burning of the gases in different chambers. That was the additional idea. But then you had many tubes and ducts with hot gas always causes problems. Not in the first year, not in the second year, but after the third or fourth year, things get really tricky if you use too many ducts. And I said, I don't want that. And I don't want any combustion chamber heated up with liquid gas. I don't want any burning chamber at all. I just want to have a reactor. It can be as easy as that. And the reactor only consists of a closed tube that leads to the burning chamber. And then the char is pushed onto a conveyor belt and is transported out. And the gas escapes to upwards and is burned. And if you deal with pyrolysis before you think about anything, you should know the oven of Stephen Joseph. For 30 years, he worked with biomass charring and pyrolysis, and his latest development is a Contiki with throughput process. It's just a burning chamber with a transporting system pushing the material through, and the oxygen can't go down. I have a direct heat transfer from the flame, and I can run small systems with a high throughput. And this system also has a disadvantage. and that is no heat reaches the material at the bottom, and you have to whirl it, you have to mix it, a high number of revolutions of the system so that everything is heated equally. And this is a difference, a disadvantage we compensated for. So we have used our experience and based it on Stephen Joseph and Biochar. So the system is one thing, the facility as such. But what is equally important is the concept that is underlying, because we're not only talking about pyrolysis, but what else is happening? This is our concept that we used as a blueprint for composting systems. This means you need absolutely dry feedstock. It doesn't make sense to introduce a wet or moist substance. That was the idea of the past. What system can use moist material? That doesn't make sense. It needs to be dry. We have enough energy per line, 300 kilowatt to dry the feedstock. It's then introduced into the stove or the oven. The tube isn't fully closed. The last third part is opened, is widened. The material is pushed through slowly. This leads to a gradual heating, and then at the end, the flame energy is applied onto the material, and with that, we can increase the throughput. The hot exhaust gas is suctioned away to the top, and it's cooled by air to 300 degrees. I don't want to cool with air. That's my appeal. I want to have an ORC in the middle. If somebody has an idea of how I can lower the degrees from 900 to 300 with ORC, please get back to me after the presentation and I'll invite you to coffee. What do we do with the 300 degrees hot exhaust gas? We introduced it into a sewage sludge dryer by Jumbo. This is a proven system that was developed for biochar development for drying purposes. And the good thing is the extremely high efficiency. We introduce wet sewage sludge. We mix it up to 70% of dry mass. It's a kind of a fluidizing bed. The material is thrown upwards and hits 300 degrees hot exhaust gas. And this has a very high drying efficiency. There's a lot of water that evaporates very fast. Then we have got 3 different chambers, and then it is exits the system. And we do contractual work. There's a new regulation, waste use regulation, and all the sewage sludge needs to be burned, and our systems need that. We offer the service to do that. The flue gas is 100% moist and 70 degrees warm. We can reduce the temperature to 40. What happens if you condensate the water? The energy comes back. This means we have a dual energy use during the sludge drying process, then condensate it out, and then the low energy temperature is used to heat all the buildings we have. So the thermal heat use concept is very important. The condensate goes to a sewage plant, and then we also have a lot of nitrogen that comes out of the sewage sludge, and I need this nitrogen to load the biochar ammonia sulfate production. This is applied to the biochar, and if we don't need it all, we sell ammonium sulfate. We produce a lot of it, nitrogen that we can extract before the combustion, the incineration process. And then at the end, we've got our biofilter. And that's it, biofilter cleaning. This system was approved, and listen up, without any flue gas measurement. We don't need any permanent measurement because it's impossible to have pollutants in the exhaust gas. Nothing can happen. The sewage sludge drying process is our cleaning process. All the elements that might be hazardous are eliminated. In the original state, sulfuric acid is even introduced so that it doesn't get too alkaline. We have a dust filter included, and we extract the nitrogen. And the latest discussion we've had, NOx. I'm sure there is NOx. And I need to say thanks to Stephen Joseph. At this point, where the fabricated biochar is in the oven, in the furnace, if you apply water, pure hydrogen is produced. And this is our reducing agent for nitrogen. It works better than urea. So this means you can reduce NOx to any value close to zero. So this means pollutant emission is impossible in that system. This is Pyro 3 made by NGE. This company has introduced our system to the market. And if you're interested, what's important is everything that's around the actual setting. We'll invest 7.3 million into this first stage with one line, and then we will enhance it to 3 lines, expand it to 3 lines. That will be the final scenario. Let me briefly touch on the costs. 1 ton of biochar, how much has it cost so far in all years? These are the actual costs of the last 10 years for us. And you see a slight problem because the system was destroyed several times, reactors needed to be exchanged. So the numbers go down in 2022, but the production costs 1,200 euros. That's not funny. And in this new system, what does biochar cost us? Without any thermal use or anything, if you just put the system 1 ton would cost 1,400 euros. We get some subsidies. That doesn't even compensate the price increase that happened last year, but we are still happy about the subsidy. And as we have this sewage sludge drying process, this gives us back a lot of money. We also sell CO2 certificates, 150 euros per ton. That's a very low calculation. We are always on the safe side with that. And we have 30 cents of energy costs. I'm sure that this will go down again to 50 cents one day. And if we produce it ourselves, we are also at 15 cents. This means that the production costs are around 400 to 500 euros per ton. And things get interesting if once we can implement the second and the third line. This is when biochar production is fun because of the results you can generate money-wise. And the industry needs to accept that biochar production will develop in that way, price-wise, and not everybody will survive. These are the costs without feedstock. And if we use chips, you also have to add 420 euros. This brings us to the actual production costs. And this brings me to the summary. Producing biochar is relatively easy. We know how to do it. Many parties can do that. It is more difficult to develop products from it, and it is even more difficult to market these products. That was the priority in our last 10 years, developing products from biochar and market them. But there's one thing that many people haven't seen yet. Production costs, that's one thing, but the consumer costs for the consumers, that's another thing. And there's a factor of 3 in between that. We need warehouses, we need a retail structure, we need mixtures, and so on and so forth. Don't believe that if you can produce at 1,000 euros, you can sell it at 1,000. That's nothing that will sustain you. This is why I thought about whether or not to say this or not. There is the risk, the danger that the production is self-destructing if we don't take that into account. We will survive because we don't have to pay anything for the feedstock, because we can market the thermal production perfectly, because our system has the right size, because we will be self-sufficient regarding energy production unless somebody comes and introduces ORC into our system. For 10 years, we've invested massively in product development, and because we have the customers, we will survive. We are currently not only marketing our 150 tons of biochar we produce ourselves, but another 1,000 to 1,500 tons that we buy because our market is export-oriented. This is our system. This is what it looks like, and it is being built in a CO2 neutral manner. I think it's a sign of hypocrisy if you sell CO2 certificates for biochar, but I have emitted a huge amount of CO2 to produce the system. That should have been counted. We use the CustoCom, the climate add system. We will have concrete built in that's close to CO2 neutrality, and the whole hall will be made of wood. What else would be possible? Thank you very much for your attention. It was very impressive. You talked about much more than the actual product. Are there any questions from the audience? Björn Kunze of Carboforst, thank you very much for this very interesting and inspiring presentation that shows us where the weaknesses are. And there are plenty of them, obviously. I have a question on sewage, on wastewater treatment. I understood that you want to avoid NOx emissions and that you can reduce it with hydrogen. But I haven't understood, and please can you explain how you want to do the following? Hydrogen, how do you want to bring it to the NOx without it developing into water steam, without it oxidizing in the process? Thank you for that question. I don't know how it's done. Stephen Joseph proved it. It goes down to 6 milligram NOx. We have 200. Somehow it works. I'm not a chemist. I'm not a chemist, but please just try it out. If there are no questions from the audience, I would like to know the following. Nicolas Feudel, I saw the horizontal bed cam. That was more like a baker's oven, but he used the same principle, slow throughput of the biomass. He had different position possibilities that he had built in, but this here seems similar. This means you can do without pelleting the fine material, as I've seen it, because there are no, although the transportation is faster. Our conveyor belt isn't fast. I know Nicolas Fördel's concept, and I looked at it. His problem was that he didn't really implement a single oven. Stephen Joseph, we looked at the latest furnace he produced, and I need to see things live before I believe it. And the concept was convincing, but it hadn't been implemented in practice. A question from the audience and then an online question. Thank you very much, Gerald, for this great presentation. This is really pioneering work. It's really surprising what you achieved. And that deserves an applause. I've been part of that since the beginning, and Gerald has been working in this field for much longer even, so that's great. I have a very different question. The sewage sludge trying. Did you have any problems with permits or bad smell, pollution? I can imagine that in an urban environment, if it's in an industrial area, for instance, that might be a problem. This system, I would build it here outside this hall. It is so sophisticated that nothing can happen. We also looked at the posterior processing of the waste. We have a biofilter condensation trial in our city, and the system is in the city center. It's a wastewater treatment plant that also does this kind of treatment, so they can really handle it well. I wouldn't be worried about any of that. Great. We don't want to neglect our online participants. Thank you. Jonas Weiss would like to know if you also have experience with compaction of input materials. We have tried a lot with pelleting because dust is the main problem with our facility. Burek, the company, solved it. We have a hot gas filter that we will build in. We don't have it yet. This is why we've pelleted a lot of material. The spelt husks as well. And in our pelleting process, wear and tear was really high, and we discontinued fast. If you use pelleting, that works. But I think doing something else is a lot of work. You need to develop a system in a way that dust can just go through the system. A follow-up question on that. What is this throughput that is scheduled, and how is the sewage sludge transported to you? The throughput of the pyrolysis system is 2,000 tons of feedstock per year. 700 tons of biochar will be the outcome, and then 3 times more with 3 lines. How do we get the sewage sludge? It arrives by truck. I mean, how else would it arrive? No, but from what distance? In the Burgenland region, they use it for agriculture. Everything is put on the field right away. So we receive it from Lower Austria, let's say 100 kilometers. I stress the 100 kilometers with one exception. We also receive sewage sludge from Slovenia. This has been a strategic decision in order for the price to not drop too fast. We also have 200 kilometers as a distance where we get the sludge from. In order to be economically viable, and survive, that's necessary. I'm sure there are many questions. One more. Okay. We have to allow our host in Darmstadt to ask a question. Thank you. If I've understood you correctly, you spoke about the input. The sieve overflow, you measure it. Well, through the washing process, we can guarantee that there are no stones in it. And stones in a reactor and in a screwed conveyor belt cause problems. Or you would have to need to apply a very different design. It's much safer the way we do it. So the question was about washing and stones. And I need to think about what do I do with biochar and the stones afterwards. We have a very fine grinding process afterwards that's downstream, and stones in it don't really help in that process. So I need to take the stones out.